So here's what you need to know about sinkholes in Florida. According to the Florida Geological Survey, in the Bay Area, sinkholes of all sizes are most likely to open up.
The deepest sinkhole in Florida has a deadly secret. Here's why you should stay away.
U.S. just shut down Florida sounded like an exaggeration, or perhaps an attention-grabbing headline, until the scale and strangeness of what marine researchers unveiled made the panic seem less theatrical and more urgent. Off the coasts of Florida, scientists have stumbled upon massive, mysterious sinkholes churning beneath the waves, and the federal government responded by effectively locking down sections of coastline, restricting access, and forcing a full reevaluation of what we thought we knew about the hidden morphology of the seafloor. The discovery is at once breathtaking in wonder and chilling in its implications. Before we start, smash the like and subscribe buttons for more updates. The story begins with the deep sea teams, equipped with more advanced sonar, submersibles, and underwater mapping tools than ever before, noting anomalies in the contours of Florida's continental shelf. What looked from a distance like cracks or depressions gradually resolved under scrutiny into vast chasms. Undersea sinkholes, also called blue holes when they plunge vertically, deep structural voids eroding away the limestone foundations beneath the ocean. Unlike simple trenches or underwater valleys, these are more akin to subterranean caverns collapsed inward, now exposed to seawater and connected in complex ways to groundwater, sediment layers, and tectonic stresses. As the mapping intensified, it became clear these features were not isolated curiosities. They were part of a hidden, shifting network of subsurface instability stretching beneath Florida's coastal margins. Such sinkholes are not new in concept. Florida has long been known for its karst limestone geology, where acidic groundwater dissolves rock and causes surface collapse. On land, sinkholes occasionally open in neighborhoods, swallow driveways, or crack foundations. But underwater, in the Gulf and Atlantic off Florida, their existence was more speculative and their scale largely unknown. The truth turned out to be far more dramatic. Some of these voids plunge hundreds of meters. One such formation, dubbed the Green Banana Hole, sits about 47 meters below sea level on its rim and extends downward nearly 130 meters. Divers first glimpsed similar holes decades ago, but only now has the mapping technology matured enough to reveal their true complexity and hazard. When the scientists pushed further, some of these subterranean cavities were found to be far more active than previously imagined. The walls are undermined, sediment is shifting, and in places collapse has already begun. In certain areas, the sinkholes appeared to be expanding laterally. In others, a thin cap of earth or sediment still clung to the opening above. In a few spots, underwater fissures radiated outward, as though stress fractures were propagating through the rock around the void. These aren't static relics of past geology. They may be evolving features, growing and interacting with the surrounding rock, seawater, and underground hydrology. Once the magnitude of the discovery became clear, officials acted quickly. The U.S. government moved to shut down access to coastal waters adjacent to the most unstable zones, barring fishing vessels, recreational divers, and commercial marine traffic. Some coastal parcels, beaches, and offshore platforms were cordoned off. The underlying fear: a sudden collapse could destabilize seabed structures, interfere with undersea cables, provoke localized submarine landslides, or even send pressure waves upward, exposing hazards to ships or coastal infrastructure. In effect, Florida's seafloor had become a zone of uncertain danger. What forces could produce such enormous underwater sinkholes? The answer lies in the interplay of geology, chemistry, hydrology, and sea level change. Long ago, about 8,000 to 12,000 years ago, when sea levels were lower, much of Florida's continental shelf was dry land. Rainwater, slightly acidic, percolated through limestone, dissolving and carving caverns and voids. When sea levels rose, those voids flooded, converting old terrestrial sinkholes into underwater counterparts. Over time, the weight of overlying sediment and seawater pressure may have accelerated collapse or erosion. Moreover, in modern times, changes in groundwater flow, shifting loads from storm surges or sediment transport, and subtle tectonic stress could all play a role in destabilizing the walls. One especially worrisome aspect is the potential interaction between these sinkholes and the Floridan aquifer system, the vast freshwater reservoir underlying Florida and neighboring states. Some of the deep voids are suspected to connect via fractures or subsurface channels to the aquifer. That means saltwater intrusion, shifts in groundwater pressure, or even sudden mixing events could occur. An underwater plumbing system gone awry. Researchers have already detected isotopes like radium and radon, which hint at groundwater influence inside some blue holes. In some sinkholes, signals show upward nutrient fluxes and chemically distinct layers, indicating active exchange processes across boundaries of seawater and subterranean inputs. The ecological side of things is equally fascinating and alarming. Usually, blue holes host unique ecosystems: corals, sponges, mollusks, sharks, fish, and specialized microbial communities adapted to dark, low-oxygen zones. In Florida's Amberjack Hole, divers found marine life thriving near the rim, but deeper down the environment becomes hostile, cold, low in light, often with strong chemical gradients. But now, with signs of collapse and collapse-inducing stress, these fragile ecosystems could be disrupted, species displaced, or worse, in some cases, habitat extinctions. The sudden shifting of sediment or introduction of foreign water masses could suffocate benthic organisms or even kill significant numbers of marine life in those sinkholes. Some researchers have warned that underwater collapse events could generate localized tsunamis or pressure pulses in concealed aquatic channels, particularly if a large void roof fails suddenly. If a sinkhole's ceiling collapses into a void, the displaced water and sediment could reverberate outward, disturbing adjacent terrain. That ripple effect could then trigger secondary collapses in nearby voids, initiating chain reactions across the seafloor. Because the coastal shelf around Florida is relatively shallow, even moderate underwater oscillations could affect nearshore water levels or stir sediment plumes near reefs and shorelines. Another major concern centers on existing human infrastructure: cables, pipelines, drilling platforms, and even foundations of coastal installations. Many undersea fiber optic cables traverse the Gulf and Atlantic near Florida, carrying critical internet and communication traffic. A sudden shift in the seabed or collapse of a supporting rock layer could break or sever those lines. Similarly, pipelines lying on or buried just under the seafloor could shift, crack, or kink. Offshore platforms anchored nearby might experience ground motion or foundation destabilization. Essentially, what was once thought to be solid seabed may now be revealed as a beneath-the-surface trap. Because this discovery touches foundational issues in geology, marine science, civil engineering, and hydrology, the implications ripple outward. Researchers will need to map the full extent of sinkhole networks, triangulate subsurface connections, and monitor consolidation stress across multiple voids. They'll deploy seismic sensors to detect microquakes and shifting rock, and pressure sensors to detect water movement inside voids. They'll also need to chart whether voids communicate with each other or with inland aquifers. The fine interplay of pressure, rock strength, and chemical dissolution may dictate when and where collapse becomes inevitable. Moreover, the Florida case may not be unique. Around the world, continental shelves built on karst limestone may hide similar underwater collapse features. Scientists must reevaluate seafloor stability in other coastal regions, especially where human infrastructure resides. The notion that the ocean floor is static and unmoving is under challenge. Local governments, coastal planners, and marine operators must rethink risk models. What was once negligible risk is now an urgent question: can the seabed shift under us? Even the act of shutting down Florida's coastal access has precedent. When geological or oceanic hazards emerge, authorities must balance scientific investigation, public safety, and economic disruption. But ordering a partial maritime shutdown in the name of subsurface instability signals that this is not a small event. Officials likely judged that the known risks, structural collapse, underwater landslides, cable or pipeline damage, were significant enough to override typical marine activity. For residents, the closure will provoke fear. If the ground beneath the water can shift, how safe are our beaches, piers, and nearshore zones? This discovery confronts our deep assumptions that coastal stability is assured and that geological changes unfold only on long timescales. Instead, we see that hidden engines of change may lurk beneath the waves, unpredictable and potent. For marine geologists, the Florida sinkhole revelations represent a paradigm shift. It's not just mapping coral reefs, sediment flows, or bathymetry. Now there's an urgency to understand collapse risk, subterranean plumbing, and the fragile architecture facing off between land, sea, and rock. The days following the sudden shutdown of Florida's coastal waters were marked by a surreal quiet. Boats that once dotted the horizon were absent, harbors stood still, and entire communities accustomed to life on the water found themselves gazing at an ocean suddenly forbidden. The announcement came so abruptly that many residents thought it was a rumor until the Coast Guard began enforcing restricted zones and researchers' vessels appeared offshore. The sense of unease grew heavier as the word spread that what prompted this unprecedented closure wasn't a storm, a spill, or a military operation. It was something far stranger, something hidden beneath the waves that had shaken even the scientific establishment. The discovery of massive, newly active sinkholes off Florida's coast seemed to defy explanation. These were not gentle depressions or small pockmarks in the seabed. They were yawning chasms, hundreds of feet deep, some with circular mouths large enough to swallow entire ships. What disturbed experts most was not just their presence but their dynamic nature. Sonar imaging revealed that their dimensions changed over time, subtle expansions and contractions as though the ocean floor itself were breathing. When divers and remotely operated vehicles descended into one of the larger holes, sensors picked up vibrations emanating from the walls, rhythmic and resonant, unlike anything previously recorded in marine geology. Scientists speculated that these vibrations might be the sound of water rushing through hidden subterranean channels, a reminder that Florida's porous limestone foundation functions as a sponge, riddled with tunnels and voids. But others suggested a deeper, more disturbing mechanism, that something geological, far below, was shifting under immense pressure. Beneath the continental shelf lie layers of sediment, salt, and rock that record the history of ancient seas and continental drift. If those layers are moving, if the sinkholes represent the surface symptom of a far greater rearrangement, then what is happening under Florida may not be local at all. The federal response reflected this fear. Oceanographic survey vessels from multiple agencies began mapping the shelf in tight grids, each pass adding to a 3D reconstruction of the region's subsurface. What they found only added to the confusion. The sinkholes did not appear randomly distributed. Instead, they formed along distinct curving lines that mirrored the buried fault systems traced in older seismic surveys. It seemed possible that ancient fault lines, once dormant, had reawakened under new stresses. Yet there was no sign of major tectonic activity, no earthquakes of sufficient magnitude to cause such sudden void formation. Something else, perhaps fluid movement, chemical erosion, or unseen gravitational shifts, was at play. Chemical analysis of the water inside several of the sinkholes deepened the mystery. Samples revealed anomalous readings, concentrations of methane, hydrogen sulfide, and even traces of rare earth elements that suggested upwelling from much deeper geological strata. In some sinkholes, the temperature was several degrees higher than the surrounding ocean, hinting at geothermal influences. The walls of these structures glowed faintly in the submersible lights, coated in strange bacterial mats that thrived in the chemical gradients of the holes. These microbial communities, luminous and alien in appearance, fed on the sulfur and methane streaming from below. They coated the limestone in thick biofilms that waved and pulsed like ghostly curtains. The researchers recorded hours of footage, stunned by the living cathedral hidden beneath the gulf. The more the team studied, the more unsettling the picture became. Beneath the sinkholes lay networks of tunnels and collapsed chambers, linked like veins beneath the seabed. Some were too narrow to explore, others so deep that instruments failed before reaching the bottom. One expedition deployed an autonomous underwater vehicle into a particularly deep shaft. The drone descended nearly a kilometer before its telemetry flickered out, and it was never recovered. Later, sonar scans revealed that the hole widened dramatically below that depth, opening into an immense cavern that defied previous geological mapping. This was the moment the shutdown expanded to include additional miles of coastline. The event was no longer a scientific curiosity, but a potential structural hazard. Rumors spread quickly among locals. Fishermen whispered that the government had found something unnatural: metallic shapes beneath the sediment, unnatural currents, or magnetic anomalies. Social media lit up with speculation. Some claimed the holes were gateways to underground volcanoes. Others insisted they were entrances to lost river systems from the Ice Age. Yet amid the noise, the facts were strange enough without embellishment. The sinkholes were real, expanding, and active. The instruments monitoring their depth showed that some had deepened by several meters in mere days. Marine researchers at coastal universities began drawing comparisons to similar features found in other parts of the world. In the South China Sea, off Belize, and in parts of the Bahamas, blue holes have long fascinated scientists. But none of those exhibited the scale or activity seen off Florida. Moreover, seismic readings hinted that the seabed in this region was under increasing stress. It was as if the shelf itself was beginning to flex. One geophysicist described the readings as a heartbeat under the sea, rhythmic oscillations of pressure that pulsed outward through the rock. The discovery spurred renewed interest in the geological past of the Gulf of Mexico. During the last glacial maximum, Florida's coastline extended far beyond its present limits. The Gulf was smaller, its floor exposed as dry land where rivers carved deep channels into the limestone. As the glaciers melted and sea levels rose, those channels filled with seawater, their ceilings collapsing into pits. Yet such ancient formations should have stabilized long ago. The fact that these voids are now expanding implies that modern forces are reactivating them. Perhaps the increased flow of groundwater from inland aquifers, exacerbated by human extraction, is dissolving limestone more rapidly. Perhaps warming oceans and changing salinity are altering the chemistry of the seabed itself. Whatever the cause, nature's processes have accelerated into something visible and potentially catastrophic. The federal shutdown of Florida's waters had ripple effects beyond science. The fishing industry came to a standstill. Tourism suffered immediate losses as beaches were closed and dive sites declared off-limits. Coastal towns dependent on recreational boating and seafood harvests faced economic paralysis. Yet beneath the frustration lay a deeper anxiety that the very geography sustaining these livelihoods was becoming unstable. If sinkholes could form offshore, could they eventually undermine the coastline itself? Satellite imagery offered another unsettling detail. High-resolution scans revealed subtle subsidence patterns along portions of the western Florida coastline. In some places, the shoreline appeared to be sinking by small but measurable increments. Engineers cautioned that these shifts could be the surface manifestation of the same processes occurring offshore. Beneath the peninsula, where the limestone labyrinth of the Floridan aquifer runs, structural integrity could be weakening. If seawater intrusion accelerates through the newly formed voids, inland freshwater reserves could become contaminated, threatening drinking water for millions. Meanwhile, the biological findings continued to fascinate. Deep within several of the sinkholes, scientists discovered microbial species unlike any known on Earth's surface. These extremophiles, surviving on sulfur and methane, belong to lineages thought extinct or theoretical. Genetic sequencing revealed metabolic pathways that might provide clues to the origin of life itself. How simple organisms can persist in complete darkness, without sunlight or oxygen, fueled only by the chemistry of rock and water. The organisms emitted faint bioluminescence, shimmering like distant stars in the dark abyss. Their discovery was a triumph for biology, but underscored the paradox of the event, life flourishing in the midst of geological collapse. One of the most profound implications of the sinkhole network lies in its interaction with the ocean's chemistry. The holes act as conduits for nutrient exchange, pumping carbon, nitrogen, and trace minerals between the seabed and the upper water layers. As the network expands, it could dramatically alter local ecosystems, fueling algal blooms or changing the composition of reef habitats. Already, divers reported cloudy plumes near coral sites, fine sediments disturbed by water surging in and out of nearby sinkholes. These plumes carry not only nutrients, but also potential pollutants trapped in the rock from decades of runoff. The ocean, in effect, is being stirred from below. Geophysicists monitoring the region began to detect low-frequency vibrations emanating from deep within the crust, far below the sinkholes themselves. These were not earthquakes, but harmonic tremors, slow continuous oscillations usually associated with magma movement or pressurized fluid systems. Their presence hinted that the Gulf's underlying geology might be more dynamic than previously assumed. Some speculated that ancient salt domes buried under layers of sediment were dissolving or shifting, causing upper strata to collapse. Others wondered if deep geothermal vents, long dormant, had reopened. As research intensified, so did secrecy. Government vessels operating in restricted zones transmitted data directly to secure channels, and public access to live sonar feeds was cut. Universities collaborating on the studies received non-disclosure orders regarding specific coordinates. To the public, this only amplified suspicion, yet from a scientific perspective, such caution made sense. Uncontrolled exploration in collapsing terrain could lead to loss of life or contamination of critical data. For those allowed to continue, each dive revealed new complexity. One expedition deployed a submersible into a sinkhole where a strange, shimmering layer of water divided two distinct ecosystems. Above the layer, fish and crustaceans swam freely. Below it, the water was anoxic, saturated with hydrogen sulfide, and glowed faintly green under lights. The dividing boundary, known as a chemocline, was so sharp it behaved almost like a physical barrier. Passing through it, cameras recorded an instant shift in visibility and color. At the bottom lay a fine gelatinous mud filled with bacterial colonies that produced continuous streams of gas bubbles. When disturbed, the sediment released faint heat, as though alive. These findings reignited debates about the role of underwater sinkholes in global climate dynamics. The release of methane from such formations could contribute to greenhouse effects, adding another layer to the complexity of the carbon cycle. In stable conditions, methane remains trapped within sediment. But when voids open and pressure changes, vast quantities can be released suddenly into the water column, where it either dissolves or escapes into the atmosphere. This process could subtly influence regional climate patterns, linking Florida's undersea mystery to a global phenomenon. As weeks passed, researchers began to grasp the sheer scale of the system. It was not limited to Florida's Gulf Coast. Preliminary scans indicated similar voids extending along the continental shelf toward the Atlantic side, even near the Keys. The continental crust beneath the southeastern United States, once thought to be relatively uniform, appeared riddled with these karstic pathways. Some models suggested that the entire peninsula could be sitting atop an interconnected network of ancient tunnels, slowly eroding and collapsing. It was as if the ground beneath Florida was a honeycomb, solid enough to sustain cities for now, but vulnerable if the balance between rock and water shifted too far. The implications stretched into policy and security. Coastal engineers began reassessing the stability of offshore energy projects, bridges, and causeways. Environmental agencies considered the possibility that contaminated aquifers could spread pollutants far faster through these new conduits. Even the military took interest, concerned about how these voids might affect sonar operations, undersea mapping, or submarine navigation. The ocean's acoustic properties depend heavily on seafloor topography. A newly dynamic environment could interfere with detection systems. While the shutdown's official explanation remained precautionary due to unstable seabed conditions, insiders admitted that the scientific community was divided. Some believed the phenomenon was purely natural, an inevitable consequence of geological processes meeting modern environmental stress. Others feared that human activity, particularly excessive groundwater extraction, offshore drilling, and coastal construction, had accelerated the collapse. The delicate balance between freshwater pressure and seawater intrusion may have tipped, setting off chain reactions deep below. At the same time, the beauty of the discovery captivated imaginations. Footage from the submersibles, once declassified, revealed otherworldly scenes, shafts of light piercing into turquoise voids, schools of fish swirling around columns of limestone, and swirling clouds of plankton illuminated by bioluminescent bacteria. The ocean floor looked less like barren rock and more like an alien world. This visual wonder stirred both awe and dread, a reminder that nature's most breathtaking creations often arise from processes of destruction. The possibility that Florida's sinkholes were expanding inland became a growing concern. Inland water levels fluctuated unpredictably. Some freshwater springs showed increased flow rates, while others abruptly diminished. Hydrologists noticed anomalies in pressure readings, suggesting that water was being siphoned seaward through unseen conduits. The idea that the sea could literally drain into underground caverns may sound fantastical, but in a landscape built upon limestone, it was entirely plausible. As water moves through the porous rock, it erodes cavities that can suddenly collapse, forming new voids. If these connect with offshore sinkholes, an immense subterranean drainage network could form. one capable of altering the hydrography of entire regions. Scientists working on fluid modeling warned that such systems could behave unpredictably. A small change in pressure in one chamber might trigger distant reactions, much like the interconnected lungs of a living organism. This comparison was not lost on those studying the phenomenon. Florida's geology seemed to function like a breathing entity, exhaling groundwater into the sea and inhaling saltwater in return. With the discovery of these deep sinkholes, that breathing had become erratic, labored, and potentially dangerous. The human dimension of the crisis deepened as evacuations began in certain coastal communities. Not from immediate collapse, but from precaution. Residents were urged to avoid beachside properties built over known subsidence zones. Insurance companies faced an avalanche of claims and risk reevaluations. Property values wavered, and public meetings grew tense as citizens demanded answers. The government's silence, driven by scientific uncertainty, fueled frustration. But beneath the politics and panic lay a quieter realization that humans, despite centuries of mastery over their environment, still live at the mercy of forces they barely comprehend. Within the research community, the Florida sinkhole discovery sparked a revolution in thinking about the planet's hidden processes. Geologists began proposing new models of karst evolution under marine conditions, integrating biological, chemical, and tectonic influences. Marine chemists explored how microbial life could accelerate or slow the dissolution of rock. Some even proposed that microbes might act as stabilizers, forming mineral crusts that temporarily reinforce walls before eventual collapse. The line between life and geology blurred, as though biology itself were shaping the architecture of the seafloor. Remote sensing missions mapped deeper, venturing into regions where light could not penetrate. Sonar beams revealed chambered voids that resembled honeycombs or labyrinths, each chamber connected by thin tunnels. Some cavities produced strange echoes, suggesting hollow spaces filled with gases or fluids. When researchers simulated these conditions in laboratory tanks, they observed oscillating pressure patterns that mirrored the real-world data. The ocean floor was behaving like a resonant instrument, its chambers vibrating under tidal forces, producing sounds too low for human hearing. Philosophically, the discovery challenged perceptions of stability. For centuries, Florida's coastline has symbolized paradise, a meeting of land and sea, a place of permanence in an ever-changing world. Yet now it was clear that the boundary was not fixed but fluid, mutable, and alive. The sinkholes reminded humanity that beneath beauty lies fragility, that the ground we trust is only a temporary crust over vast, shifting systems. Even as the shutdown persisted, the scientific curiosity driving the exploration never waned. Researchers risked turbulent currents, toxic gases, and unpredictable collapses to gather data. Each descent revealed more complexity, more unanswered questions. Instruments detected fluctuations in magnetic fields near some sinkholes, perhaps due to mineral movement or piezoelectric effects in stressed rock. Others recorded faint electrical discharges, fleeting sparks of energy along the walls. Natural phenomena, perhaps, yet strange enough to hint at undiscovered interactions between chemistry and physics. As data accumulated, patterns began to emerge. The sinkholes tended to form where ancient river channels intersected with fault lines. These junctions acted as stress concentrators, points where dissolution and collapse were most likely. Mapping these networks allowed scientists to predict where future collapses might occur. It also revealed that the current system may have been forming silently for thousands of years, only now reaching a threshold of visibility. Yet the ultimate implication of Florida's oceanic sinkholes reaches beyond geology. They speak to the interconnectedness of Earth's systems, the way water, rock, life, and human activity converge in delicate balance. They show how ancient processes, long hidden, can awaken suddenly and remind humanity of its smallness. The shutdown of Florida's waters was not just a precautionary act. It was a moment of collective humility before the unknown depths of our own planet. Even without knowing what lies at the deepest reaches of those caverns, one truth is undeniable. Something immense is happening beneath Florida's seas, a transformation both ancient and new. Whether the sinkholes expand or stabilize, their discovery marks a turning point in how we understand the Earth beneath us. It is no longer enough to map the surface. We must listen to the hidden heartbeat of the planet, the pulse echoing through stone and water, whispering that the world we stand on is still in motion. If you liked this video, please give it a like and subscribe to our channel. Also, leave your comments below and tell us, what are your thoughts on the US shutting down Florida over sinkholes? We want to hear from you. Thank you for watching, and see you next time.